but he's even well known for his contributions to the practice as well as the technology of finishing processes. And he has worked, has been a leader in the industry, working with Norton, and later I think it became Saint-Gobain. And he has mentored a lot of people, both in the industry as well as academia in this front. And in the last 10 years, I have known him as a collaborator with Professor Ramesh Babu, and actually being able to translate some of the research as well as technologies which are at lower technology readiness level into actual practice. And I really enjoyed learning about the intelligent machine tools that he built as part of Micromatics. And one of the reasons why I would like to have him as part of our part of our project meetings is to learn from him about some of his vast experiences, especially in translating, or what it takes to translate some of these technologies, and how we can think about our research so that they are easily translatable to industrial practice and create value.
So the case studies, there are several of them I have listed here, and I could list another 4 or 5 more out of my career. But let me just pick one of them: grinding of thin film heads for magnetic recording applications, data storage, or computer industry, for new business development. So you may wonder, how is this guy coming from the grinding background, which is usually seen in the automotive, aerospace, or bearings, or at best making hypodermic needles or something like that? What's he doing in the computer industry? The point here is science, once you understand it, has got ability to permeate any number of applications across the globe. And that is where innovation and opportunities come for those with a scientific background. So the example I'm going to show you here is one where I told you that we started essentially with understanding the grinding of ceramics. We didn't not even have an idea of where we will use it. But once we have perfected the understanding of the grinding of ceramics, which took us about 3 years, then we had to find out where the use is. And we found out there was some use for magnetic thin film head manufacturing. And then the product is what we came up with, which you'll see. In order to make the product, there are so many things in the process that had to be modified. But once the product is modified, let me move it here. Once the product is modified, through the process, it had to be used. Through use, we found out some needs, and this interactive story is what I'm going to tell you now. Okay, so system thinking is then engagement in all parts of the system, simultaneous impact in all 3 dimensions: the input, output, product, process, and use, and also having a simultaneous impact on science, engineering, and management. Now, do not think when I say this, it's so complicated. How can I do all these things? You see, the power of our brain is so good that you can do all of these things in parallel, as long as we let our mind be free to do what we want to do, as opposed to be constrained by what we are told we should do. What is the science of grinding? In fact, this model for science of grinding can be used for any number of applications. First of all, if you think of any abrasive application, you've got an abrasive producing a chip, and then abrasive, if it's not producing chip, it is plowing or displacing the material, or sliding on the work material, or the chip that is sliding on the bond material, chip sliding on the work material, or the bond itself sliding on the work material. So it doesn't matter what abrasive application you can think of, these are the 6 interactions that are taking place all the time. So when you got 6 interactions, you've got a normal force and a tangential force, so you've got 12 vectors. So every grinding application comes down to managing the grain work, bond work tribology, machining cycle, grain work, bond work tribology as a function of time, chip bond, chip work tribology as a function of time, so that the 1 vector is here, 2nd is here, 3rd, 4th, 5th, and 6th. And within the 3rd vector, which is a machining, you design a grinding cycle where you have a very high force in roughing, semi-finish, finish, and so forth. When you come to spark out, you're having only grain work tribology. So in which of these 6 interactions or 12 vectors you're interested? Why? Are these time dependent? For how long? Can they be constrained to be within some limits? How and why? It's always a quiz. Can they be time independent? For how long and why? So this is essentially the phenomenological understanding of grinding, irrespective of any application. So I can walk into any application, look at the process, divide it into these 6 interactions based on the measurements we make, and based on the discussion we had on the input side, based on the discussion we had on the technical output side and the system output side, we arrive at these criteria, which of these 6 interactions of interest to why, and that essentially is the science of grinding. So essentially, 6 microscopic interactions, their magnitude and relative impact can be used as dominant mechanisms in the design and management of any grinding process. So I have finished teaching you science of grinding in 2 minutes. Okay, now let's go to science of ceramic materials. In the grinding of ceramic materials, it's the same interactions have to take place, but only difference is the grain work interaction can be cutting, will lead to brittle fracture or ductile deformation. There is hardly any plowing, or there will be a lot of sliding. And this is from the literature. The whole thing you can get it from the reference for this. Essentially what they say is, when the radius of the indenter is large and the applied force is large, it doesn't matter what you do, you'll always have cracks in ceramics. When the radius of the indenter is small, even then when the applied force is large, you'll have brittle cracks in a different kind compared to, you will also have a median crack in addition to lateral cracks. Whereas if a ductile material, whatever the radius you use, whatever the force you use, will always be deformation. But there is a sweet spot in ceramic materials where the radius of the indenter is small, the force applied is small, you end up with having ductile deformation. Now, the reasons for the will vary from the material, its fracture toughness, so on and so forth. But essentially, you're trying to operate in this regime. And if you operate only in this regime, it will be called ductile regime grinding. But on the other hand, you can always be sure, because of this interaction, there will be some interactions taking place in this direction towards brittle fracture, some taking place towards ductile deformation. But it depends upon the chip thickness, which is the volume of indentation. It depends on the force per grain. It depends upon the abrasive particle size, which influences both of them. So essentially, the more you skirt towards the left-hand side, you have ductile deformation. The more you move to the right-hand side, you've got brittle fracture. So in addition to general issues of grinding that you normally deal with, you have to manage this balance. Essentially, that's what makes a difference between ceramic grinding versus grinding of brittle ductile materials. Okay, now we have understood the science, but you have to translate that into application. That's what engineering is all about. So that same picture I showed you now becomes translated into how is it affected as per machine tool properties, processing tool properties, work material properties, operational parameters during the process and output. It'll take me some time, so I would not go into the details, but you can go to another time. So essentially, you're trying to stay mostly on the left-hand side and never go into the right-hand side. But because you can live with some degree of brittle fracture, as long as it's not substantial. And you can live with some brittle fracture and roughing, but you can get it off in the finished grinding, just like you will remove the surface roughness, which will be very coarse and rough grinding in ductile materials, and reduce that in finished grinding. Except here, you're not trying to manage the surface finish, you're trying to manage the micro cracks. And essentially, but typically, most of the literature had said ductile regime grinding operating only in this regime, but that is not economical and practically feasible. So what we took was, we took the what is available in the literature, we came up with this model, we understood that we had to stay in a certain regime. Within that regime, you can design a roughing grinding cycle and a finished grinding cycle for economics and productivity and so forth. And you could indeed achieve very high surface quality and low brittle fracture, and cracks. Now, so all the other principles of tribology apply. So you have to be a very good tribologist as much as a machine technologist if you want to be a good grinding person. So in fact, I would argue that grinding is machining plus tribology. Then machining is a subset of grinding as opposed to people thinking of grinding as a subset of machining. As a scientist, I'm not here to make politics or arguments or anything like that. But that is what science allows you to think differently from others. Now, you can once then you go crazy because scientist is also supposed to demonstrate his capabilities in areas that did not exist before. Here is A1 and A2 are two surfaces, both on the same material, except when thermal issues are not managed, it's not brittle fracture. When thermal issues are not managed, you'll end up with A1. When thermal issues are managed, you get very good surface A2. Also, you can grind very mirror-like surfaces in a cylindrical surface or a flat surface. You can take a hollow tube and grind it into worm and create a spring out of it and then collapse it like a metal spring. If a metal spring, you bounce it, you can bounce it forever, it may not break. Ceramic spring also, by the way, I have bounced it with great degree of confidence, except you bounce it 10 or 20 times, it will break eventually. But you can make ceramic springs and collapse them just like metal spring. You can grind ceramics to very thin diameter as shown in E without any end support. And you can, because the force per grain, the grinding conditions are so good that you can manage that. And because material has its own inherent strength. You can grind a silicon wafer, which is like a brittle material, and bend it into a plastic sheet of steel. You can grind a sapphire so plain and so good in surface quality that it becomes transparent. So all this research becomes useless unless there is somebody to listen to. So I took this work, I visited many companies who had a need. And just lo and behold, this is where serendipity comes. IBM, San Jose, this is where I'm living now. I made this presentation. A gentleman by name Dick Satterfield, he told me that they have a need to make thin film heads for the disk drive industry. Thin film heads are these on the tip of the arm here, which looks like this. And that is what puts the information into the disk and takes information out of the disk through inductive coils. And he said, we have to make this. But to do that, we have to make very thin slices. I don't know if you can see the slices here. This is ceramic that has been cut into those thin slices. So this is what we have to make. If you're capable of doing that, today we are doing it ferrite, which is a very soft material. We can do it with a resin bonded wheel. But this ceramic, with aluminum titanium carbide, we cannot cut it. It has got a glass in it, electric circuit in it. If you got a grinding wheel, because it's also ceramic, that will do the job, come and see me. So we came back, we made this kind of a sample, as you see in H, and took it to them. So essentially, I've done the science, you've done the engineering. Now you have to go into the application of the engineering for an intended use that's not fulfilled. But you also have to make choices. It has to be an emerging market. It also requires system integration. Our common word system comes in. So this for thin film head development for this hard storage industry. So essentially what you see here is the thin film head. Now, again, there were so many steps involved in this process, but let me just stay with only the slicing portion of it. So essentially, we ended up with a grinding wheel. It's a metal bonded grinding wheel, with a thickness of 40 microns to 200 microns. These are made of powder metal composites. So they are processed for gang slicing. And this is the set here. And we did all of those things, and we had to do many things. But before that, we had to do process innovation. I can tell you so many things we had to do. We'll come to it in a minute. Essentially, in order to make this grinding process, we had to come up with a metal bond technology. And then the wheels had to be made in very large quantities. The process had to be developed for that. But when you make it, these have to be flat and parallel within micron thickness. Normally, grinding wheels are not made to that thickness. for which you had to develop a lapping process. So when we finished the lapping, we had to get a machine which was $200,000 for lapping. That division had only $1 million for the total capital spending. So here I'm a new guy in the company, and I'm telling my boss, I need a machine for 200,000. So I had to take the technician who worked on the factory floor, by name George Staten, along with me to see the vice president to say, sir, I don't believe me, but this is the man who has been with you for 25 years. He says he can make it work. And he says, with this machine, we can get a great new business. So he's not trusting me, he's trusting George Staten, who doesn't have an education, but who has got experience and trust in the company. So essentially, there are what I call emotional intelligence, I talk about later on, is part of what has to be part of the innovation. So we buy the machine, we put it in place, and then we had an R&D engineer who would not sleep unless any new specification, he has to make it tomorrow. If not, he won't go home, he won't sleep. And that was his passion. And he had a technician who will make tooling for whatever Dr. Paul Goldman wanted. This guy will make it, or Corcoran will make it, no questions asked. So we have built up a team slowly who are passionate about creating a solution. Yes, we are all looking for a job or looking for a product, but that was not the driving force. The driving force was a solution. So we had to do manufacturing. But even with that, the wheels themselves had to be made for different thicknesses. So we had to come up with a process for that. We had to have work holders, cooler ducting, so many things. Each one of them, we even had to come up with a pricing strategy because, so again, this is very closely interacting with the customer back and forth. Because Dick Satterfield tells me that after it is successful, I will need it in thousands of units. But before it's successful, I'll need hundreds of units. But when I'm testing it, I'll only need tens of units. So I'll have to find a way to meet those variety of needs and price it accordingly. And only I can do the pricing because I know the technical side, I know the engineering side. But if I give it the pricing to a traditional pricing department, they can't handle it. In fact, today, most of our supply chain solutions, if you try to make any variation, you will kick it out as non-standard. So most of the things we do as industrial research will be non-standard. So this is where most of the things that most people who do research in industry today suffer and fail because they cannot go beyond the comfort zone of engineering and into the pricing, into supply chain. All of those things are required in order for the solution to be completed. So after doing all of those things, we still were not successful because once you're doing slicing, everything was being made, productivity, everything was good, except the wafers were not plain and parallel. What do you do then? Then you find out that this horizontal spindle surface grinder we're using with a heavy spindle on it was deflecting. We had a cantilever beam. So we had to think of a way of solving the problem by coming up with an outboard support, like you do in a twin grip in a centerless grinding machine. So that resulted in a whole new invention of a new machine. Startup of a whole new company to make this kind of machines called MTI. So in the late 80s or early 90s, when everybody said machine tool industry is dying, this machine tool company came out of the ground, and that now essentially ended up with a solution where you have got a new machine tool with a new design, precision. Now we are coming back to the system description of our solution with more details in it. So you see new machine tool with a new design. Also it has to have precision because step and speed capabilities, manufacturing and distribution, custom testing, qualification support. Many of these things most machine tool companies would not offer it because they only want to make the machine and sell it. Customize the wheel fabrication for different thicknesses and spacing, gang assembly. They also have to have distribution services because IBM San Jose may want something and then IBM Mainz in Germany may want something else, on and on. But once we open our mind, we can learn all these things and accommodate all these changes. Anyway, custom wheel fabrication, gang assembly, distribution service. On the grinding wheel side, we had to come with a new design, new composition, new process, new finishing solution, pricing strategy, people, team, I told you all those things. On the component side, materials technology, they kept changing as they came closer and closer to commercial. Dedicated pull customer. That is the biggest thing. If you got a pull customer who is part of your team, wants to make it work, there's nothing better than that. like rapid growth market and many startups. And this is what you have to pick ahead of time. Just because you did research and whoever wants it, you just keep trying it. And there are lots of people who want to try because they're task oriented. You have to be system oriented and find the right partner who really wants to make a difference. And many startups were at that time. And then operational factors, so many things, work support, fixtures, process parameters, all those. When you put them all together, remember the seed for all this innovation is the science of grinding ceramics. No question about it. But once the process is developed, if you go and ask how many people can explain the science of grinding ceramic like I explained it to you today, probably a handful. Because seed is like that. It is only when it grows into a tree, which is engineering. Science is the seed, engineering is the growth of the tree, and then management is the maintaining the tree and harvesting the fruits. Sure, if we can let somebody else do the harvesting, somebody else grow the trees, and you be the seed and be complaining that you're not getting attention, or you manifest yourself as a seed, as a tree, and as a harvester, that power is well within each one of you. And the industry or the society is looking for those few, and for them, the growth and opportunities is limitless. So we ended up with a high technical output was a thin film head, and the system output was a high margin growth opportunity for a stagnant industry, because abrasives is not a growth industry. But we took a very comfortable, stagnant industry, traditional 125-year-old brick and mortar company, into a highly vibrant growth industry, high-tech industry. Of course, there are challenges. In this industry, the cycles are very fast. Today, there are thin film heads made, and because most of your storage for all your cloud computing, all the storage happens to be in these disk drives, because those solid state drives, USB drives, they're very expensive. They still cannot manage the data amount that is needed. But it's managed only by two companies, Western Digital and Seagate, and probably Hitachi out of Japan. So there will be changes. So you have to keep up with the change. But that's a different side of the innovation. So to summarize it, I told you about the system thinking, and there are a set of several transformational skills, of which I talked about the emphasis on science, I talked about knowledge integration, and I talked about end-to-end innovation. But there are others. Each one of them will constitute a seminar by itself. In fact, ideally, a course can be taught on system thinking and transformational skills, about 10 to 12 classes that will be very valuable and powerful, not only for your students, but also for people who are collaborating with you from the industry, and not only for your department, but across many departments. So to summarize then, yes, we need academic education, which you are all providing very nicely. You also need industry collaboration, because that's where this rubber meets the road. But you also need transformational skills, which is not formally taught today. And without that, we are acting only in activities that are task-oriented, and we don't have the time. You have to change reverse the direction of these arrows of doing what you're asked to do and saying, I don't have time, I don't have anything, I don't have a result, life is frustrating, to a transformational where you must be goal-oriented, where every day you do something, must have some technical output and a system output, which leads to system thinking, common language. We only had the beginning of the common language today, emphasis on science, knowledge integration. Then we go to end-to-end innovation, core technology platforms, emotional intelligence of innovation, and ecosystem development. So what I have told you today allows you to think in terms of moving away from task to goal. From there, you need to move into impact, and finally into sustainability. So as a homework assignment, because I'm talking to the university and university faculty and student, I'll leave this slide with you. Take this slide and write your own answers. And if you have questions, you can always come back to me. Develop a dictionary for the following words or their meaning. Thank you very much. And if you have questions, we can take it from here.
Again, thank you, Dr. Subbu.